All right, thank you for coming. We'll go ahead and get started. This will be on YouTube later on if you want to recap anything or you have to leave early. Okay, so we're going to just start and go through the problems. As always, whenever you want to stop me and interrupt me to ask a question about that or any related thing that you want to talk about, just interrupt me anytime. It's fine. All right, so the first one deals with work. So we have a sample of N2O expanding from 3.75 to 8.25 liters against a constant pressure of 957 torr. And we want to know what the work term is for that. So if we're asking you to calculate work, there's only one equation you need to worry about. There are other variations of this for different conditions, but we're only talking about the one that deals with work against a constant pressure. So what we're going to use is this relatively simple equation here, which is minus P external delta V, where P external is the external pressure, delta V. Delta V is the change in volume. And the part that a lot of people forget is the negative sign out in front. So by definition, work is negative when a gas expands and it's positive when a gas is compressed. So we have to keep that sign in mind when we're doing this. That's a part to remember. And so for this problem here, we notice that all the answers are given in liter atmospheres, not the standard unit for work, but typically liter atmospheres or joules is going to be the units. So the first thing we should do is convert the pressure into atmospheres. We could certainly calculate work in torr liters, but that's not a very convenient unit at all. So we'll take this 957 torr, which is the external pressure. So to review what we're going to do here, a very common conversion we'll have to do is convert torr to atmospheres by dividing by 760. So that should be something that's ingrained in your fiber now. It's converting torr to atmosphere. So we get 1.26 atmospheres is the external pressure. And then delta V, just like delta anything, is final minus initial. So we're going from 3.75 to 8.25 liters. So the final volume is 8.25. Initial is 3.75. So that's minus 5.67 liter atmospheres.
On the top you put 12.6 instead of 1.26.
I did. I got to get back in the groove. I had a bunch of other things this afternoon. I'm out of. All right, let's get back to focus, and we have minus 1.26 atmospheres. That's going to be the correct value. Give you minus 5.67. It may, in some cases, be necessary to convert this into joules, in which case, remember that 1 liter atmosphere is equal to 101.3 joules. All right, if you forget that number, remember that we have two values of R in the periodic table. So if you take the value of R that's in joules and divide it by the value of R that we use for gases, which is 0.0821 liter atmospheres, we get that 101.3 joules per liter atmosphere. So that's a conversion factor to use. And if you forget it, just divide the two values of R that are on the periodic table. Okay, so any questions on that? All right, so the next question, number 2, is a more conceptual problem dealing with delta H. So we have a reaction between HCl and NaOH. If you ever mix a strong acid and a strong base together, you do evolve a lot of heat. It's an exothermic process. So which of the following statements about this process is correct? So we have 4 or 5 choices here, I guess. We have to figure out which one is true or correct. All right, so choice A, delta H is positive. So remember that exothermic means delta H is negative. It's the opposite of that. All right, so we want to sort of link the terminology to the properties of delta H. Exothermic talks about a situation where the change in enthalpy is less than 0, negative. So that one's going to be incorrect. All right, choice B asks it in a little bit different way than we're used to seeing it. So the enthalpy of the products is greater than the enthalpy of the reactants. Now, we don't typically know or determine the individual enthalpies of the reactants and products, but if we think about what delta H means, remember that delta anything is final minus initial. So if we're talking about delta H and we're talking about a chemical reaction specifically, the final state is the products, the initial state is the reactants. So delta H is the enthalpy of the products minus the enthalpy of the reactants. As we've already determined, because it's exothermic, this value has to be less than 0. And so if we rearrange this or just think about it, that means that the enthalpy of the products in this case has to be less than the reactants. So whenever you have a negative delta H, the products have lower enthalpy than the reactants, and so that one's also going to be false. States the opposite of what's actually true. All right, choice C deals with the temperature of the surroundings. So remember that for delta H to be negative, to have an exothermic process, that means heat is released from the system, which means the temperature of the surroundings increase. So anytime you have a negative value for either Q or delta H is just a specific type of heat, Q. Anytime the value is negative, that heat is transferred to the surroundings and the temperature of the surroundings goes up. So that one is in fact correct. So we'll likely pick that as our correct answer, but let's check the other two just to make sure. The bonds in the products are weaker than the bonds in the reactants. So this one is related to choice B. So we didn't really link these two together necessarily. Remember back in chapter 3 we talked about how we can use bond energies to calculate delta E. In reality you're calculating delta H, we just didn't know what delta H was at that time. So we can use bond energies also as an estimation for delta H. So another way to approximate delta H, as we've already learned, is to take the sum of the bond energies, and this time it's reactants minus products, because when we break the bonds in the reactants, that's an endothermic process that we put energy into. And then once we reform the bonds, that's a negative exothermic process, so we subtract the bond energy of the products. All right, and because this is an exothermic process, this quantity has to be less than 0, which means that the sum of the bond energy for the products is greater than reactants. All right, so whenever this is negative, that means the bonds in the products are stronger than the bonds in the reactants. So that one's also false because that would suggest that the products are weaker, so it states the opposite. All right, so whenever you have a negative delta H, it means that you're releasing more energy when you form the bonds than you are putting in to break the bonds, and so that means the bonds in the products are stronger. So it's another way to think about that same concept. And then finally, choice E, the reaction absorbs heat from the surroundings. As we kind of already talked about when evaluating choice C, when it's exothermic, heat is released. So this is just a restatement of that, and that means that, again, that's the opposite of what's actually happening. So endothermic processes absorb heat from the surroundings, exothermic processes release heat to the surroundings, so that one's also false. So we've already found choice C as being true, but we can verify the rest are false, and that's the only one that works out. So any questions on any of those? Okay, so it's helpful to know some of the definitions and terminology associated with this, because there will mostly be numerical problems on this. I mean, as you can see from the review, almost everything is a numerical problem, but there will be some conceptual things sprinkled in. It's helpful to know. All right. Question 3, what is the change in internal energy in kilojoules when a system absorbs 965 joules of heat and has 456 calories of work done on it? And we give you the conversion. 1 calorie is 4.184 joules. I don't think I introduced this in class. If you've taken the lab, you've seen this conversion, and if you need it on the test, we'll give it to you. We're not going to expect you to memorize this conversion from calories to joules, but calories is just another unit of energy, which you've likely seen if you've taken the lab, as I said. So in this question, we're looking at change in internal energy. So that's what we call delta E. And anytime you want to calculate delta E or think about delta E, remember it's the sum of Q plus W, where Q is the heat and W is the work. And we also have to keep in mind the sign conventions for heat and work as well. So we need these two values. We need them both to be in kilojoules eventually, or joules, because the answers are all in kilojoules. So if we think about Q first, we're told in the problem that the system absorbs heat. So whenever heat is absorbed, remember that tells us that the sign of Q is positive. So the heat term is going to be plus 965 joules. Very often when we set it up in a word problem like this, we don't give you the signs of Q and W directly. You have to sort of translate the language and telling you what the sign is. So anytime heat is absorbed, that means heat is positive. If heat was released, it would be negative. So that's going to be the first term when we calculate delta E, is that 965 joules of heat. And then for work, we have work done on. That's also going to be positive. So if you do work on the system, that's positive W. If the system does the work, that's negative. So it's work done on or work done by. Those are the difference there. So work done on means it's positive. We said that the work term was 456 calories. So we have to convert that to joules to be able to add it to the Q. So it's 4.184 joules per 1 calorie. So that's 1908. So we add that together. We could also convert to kilojoules. We convert both of them to kilojoules first if we wanted to. When we add these, we get 2873 joules. If we divide by 1,000, that gives us 2.87 kilojoules. So when you're doing problems like this that ask you about change in internal energy, it's always just going to be adding two numbers together, Q and W. But you have to keep the signs in mind, and you have to make sure before you add them that they're in the same unit, obviously. All right, questions on that? Yeah? It's not coincidence. So the unit calorie was defined as the amount of heat necessary to raise 1 gram of water by 1 degree Celsius. So it's defined based on the specific heat of water, and that's why it has that relationship. Yep. Yeah, work done on is positive. If work is done by the system, it's negative. Yeah. Yeah, sorry. Well, that depends on if the volume is changing or not. So if it was constant volume, it would just be Q. Because remember, as we talked about in the first problem, work is minus P external delta V. So if you know that the volume is not changing, then that means the work has to be 0. But if it's constant pressure and the volume is still changing, then the work would be something other than 0. So it's really constant volume that would cause your work term to go away. Anything else? Okay, moving along to number 4. All right, so this type of problem, regretfully I did not cover in class. It's called a thermochemical equation. So we give you this chemical reaction, which is the combustion of ethane, and we give you the delta H for the reaction, minus 2855 kilojoules. And we want to know what is the enthalpy change in kilojoules when 12.5 liters of C2H6, measured at 25 degrees Celsius and 780 torr, is burned in air. Give your answer with 1 decimal place, no units. Now there probably won't be many questions on the test that do this, but this one really combines topics from Chapter 7 and Chapter 8. So we have a thermochemical equation, which is a balanced chemical equation with the associated delta H, and we're using properties of a gas, the volume, the temperature, and pressure of a gas to say something about that. So we kind of have to think about both topics here. So we didn't, as I said, I didn't cover this in class in very much detail, but we've seen some homework problems like this. When you have a thermochemical equation, remember that the way that we interpret a chemical equation is in moles. So 2 moles of C2H6 reacts with 7 moles of O2 to make 4 moles of CO2 and 6 moles of water. And delta H is minus 2855 kilojoules means that when that many moles of substance are reacting, you release 2855 kilojoules of heat. So you can almost think about this as just another term in the chemical equation, and you can build conversion factors off of it. So 2855 kilojoules per 2 moles of ethane, 2855 kilojoules per 7 moles of O2, and so on. So you kind of treat it as it's just another product or reactant in the chemical reaction. So that's what we have to do here, which means that whenever we're doing a thermochemical equation type problem where we're asked to either calculate the enthalpy change or calculate the amount of substance, it all revolves around moles because this delta H is related to this many moles of the substance. So the first thing we should do is figure out how many moles of our reactant do we have, in this case C2H6, which is being burned in air. We assume that the O2 is in excess because we're not told anything about it. So because C2H6 is a gas, we have this relationship between pressure, volume, moles, and temperature, PV equals nRT. So if we're going to use PV equals nRT, we need its pressure to be in atmospheres. So the same conversion we did in the first problem. We have 780 torr as the pressure for ethane. We'll convert that to atmospheres before we can plug it into the equation. So that's 1.03 atmospheres. And then so finally we can use PV equal to nRT. We can rearrange this to find the number of moles of C2H6. So it's going to be PV divided by RT. And the reason we know we have to use atmospheres as our pressure unit is because we're keeping the value of R in this calculation. R has units that include atmospheres, so that's why the pressure has to be atmospheres, volume has to be liters. All right, so when we plug the numbers in, we get 1.03 atmospheres for pressure. The volume is 12.5 liters. R is the universal gas constant, which is on the periodic table sheet. And then temperature has to be in Kelvin. We have 25 degrees Celsius. We add 273 to that to give 298 Kelvin. And that corresponds to 0.526 moles of C2H6. All right, so that's how many moles of C2H6 we're burning. We want to know what's the delta H for that, where we're going to use this chemical equation as sort of the conversion. So we have delta H is going to be moles of the reactant, 0.526. And then we're going to use a conversion factor where we're going to convert into kilojoules, and we're going to cancel out moles of C2H6. All right, so if we go to the delta H that's given to us, it's minus 2855. So that's the number of kilojoules for this reaction. And that corresponds to 2 moles of C2H6 because C2H6 has a coefficient of 2 in front of it. So we're going to put a 2 down here. Moles of C2H6 cancel out. That converts into kilojoules, and we get minus 750.9. And if this was Blackboard, you would just enter in that number there. Okay? Questions on that one? All right. See, this is one that you'll probably see something like this, so make sure we understand the ins and outs of that. All right. Number 5 is also back to related to heat. All right, so we have 5 grams of copper, which has a specific heat capacity of 0.385 joules per gram degree Celsius. It's heated to temperature of 100 degrees Celsius, placed into a cup with 10 milliliters of water, initially at 23 Celsius. What is the final temperature, assuming no heat is lost? All right, so in this type of problem, what we have is we're placing a hot object into a calorimeter, so there's going to be heat transfer between them until the temperatures are equal. So the copper is going to have some heat term associated with it. It's going to, in this case, lose heat to the surroundings. And then that heat is going to be absorbed into the surroundings. And in this case, we're assuming no heat is lost, and all we know is that there's water in our calorimeter, or just a cup of water, basically. So the heat that's lost by the copper is going to be gained by water. Now, because they have the opposite sign convention, if one of them is losing heat, the Q is positive. The other one is gaining heat, Q is negative. We have to put a negative sign on one side of this equation. We have to remember that they're equal in magnitude but opposite in signs. And so then what we do is we remember that we can calculate Q for both of these using MC delta T. This is just a physical process. It's just heat being transferred from one object to another. We're not doing a chemical reaction here. So MC delta T for the copper is going to be equal to minus MC delta T for the water. All right, and remember that what we're trying to look for here is final temperature, and then so delta T for each term is going to be the final temperature minus the initial temperature. Now it's important to remember that the two objects have different initial temperatures. That's why the heat transfer takes place in the first place. But the final temperature is going to be the same for both. So heat transfer stops once they get to the same temperature. So we only have one, unknown, which is the final temperature. So if we plug everything into these two equations here, we have the mass of copper, we have the heat capacity of copper, we have its initial temperature, and same for water. So we have 5 grams of copper. The heat capacity for copper is 0.385. Metals tend to be much smaller than water for heat capacity. And then the final temperatures are unknown, minus the initial temperature, which is 100 degrees Celsius. We can use Celsius or Kelvin for this because what we're really dealing with is a difference in temperature, two temperatures subtracted from each other. So it works either way, whether you convert to Kelvin or not. And then we have a negative sign. We have 10 grams of water. Heat capacity of water is 4.184. And then delta T for water is the same final temperature minus the initial, which is 23. I think in most cases it is. I looked over the exam questions and I don't remember if every single one has it. So that's probably one number it would behoove you to remember, is 4.184. It's given in some cases. I don't remember if it was every single one. I try to add it in sometimes if I remembered, but that's the only heat capacity you'd ever be expected to know, though. Okay, so 4.184 joules per gram degree Celsius is the heat capacity of water. So we have those two set equal to each other. And then to save myself some time, I'm going to just skip the algebra part, but you just solve for TF, and you should get something like 26.39. All right, so if you're doing a problem like this, where you're solving for the final temperature when two objects are transferring heat between each other, you can at least check your answer to see if it's reasonable. It should be somewhere in between the two temperatures. So copper started out at 100, water started out at 23. Your final temperature should be somewhere between those two values. If it's not, then you clearly messed something up. But of course, just because it's in between doesn't mean it's right, but that should be the number you get once you work out the algebra as I set it up. Okay, questions on that? Yeah. Correct. So when you set up this equation, the negative sign can go on either side. It may have been, I guess it doesn't, yeah, it doesn't really matter. It doesn't make the algebra that much different, I suppose, but sometimes it's more convenient to put it on one side or the other. All right, anything else? Okay, number 6 now. All right, so here's another calorimetry type problem, but this time we're doing a reaction in the calorimeter. So we have a bomb calorimeter with its heat capacity is 9.25 kilojoules per Kelvin, and it's filled with 1 liter of water. A 5-gram sample of acetic acid is burned in the calorimeter, which raises the temperature by 5.4 degrees Celsius during this process. Use this information to determine the enthalpy in kilojoules per mole for the combustion of acetic acid as shown below. All right, so a lot of information here. Whenever we're doing a chemical reaction in the calorimeter, the first thing we want to do is calculate the heat of the surroundings. Remember that a calorimeter basically isolates your surroundings, so that any heat that's generated by the chemical reaction will be absorbed by the calorimeter. So for that, we're going to use those heat equations, which I abbreviated as total heat, or you may have seen it as Q surroundings if you did the lab, or some other abbreviation. But it's basically the heat that's absorbed by the water plus the heat that's absorbed by the calorimeter. Now, sometimes we don't give you enough information to calculate both of these terms. Sometimes we'll either group them together or we'll assume that the heat absorbed by the calorimeter is small and so on. So you really have to use the information in the problem to guide which of these two terms you have to calculate, or in some cases both of them. Now, the way we calculate them is for water, it's the mass of water times C times delta T, just like we did before. And then for the calorimeter, it's the total heat capacity, which is sometimes abbreviated capital C, times delta T. Now, the reason you don't have a MC term for the calorimeter is because the calorimeter is made up of a bunch of different things. So you really use only MC delta T for pure substances. If you have an object like a calorimeter, you're going to just use the total heat capacity. So if we look at the information in the problem, we have both pieces of information. We know that there's 1 liter of water in the calorimeter, and we know that the calorimeter by itself has this heat capacity. So we have to include both of these terms when we calculate Q. Now, the important part of this that people sometimes get confused on is this mass here, and the only mass that you're going to use when you're calculating Q is the mass of the water. Okay, we gave you the mass of the reactant, and that has nothing to do with the heat that's calculated for the calorimeter itself. The mass is only going to be used later on, as we'll see, when we want to determine kilojoules per mole. But when you're calculating Q, the only mass you're going to use is the mass of the water in the calorimeter. Okay? So, anytime you're doing a chemical reaction, that is. All right, so if we calculate this heat term, we have to calculate the mass of water. So we're told that we have 1 liter of water. The specific heat capacity for water is in terms of grams, so we do need to convert the amount of water into grams. So this is something we should be able to do in our head, but just to walk through it real quick, we have 1 liter of water. There's 1,000 milliliters per liter, and there's 1 gram per milliliter for water. So 1 liter of water has a mass of 1,000 grams. Okay, so make sure we can convert between volumes and masses for water. The density of water is 1, so just pay a little bit of close attention to the units that we have. So we have 1,000 grams of water, 4.184 joules per gram degree Celsius is the heat capacity, and then delta T we're given directly. It says the temperature increases by 5.4, so that means delta T is a positive 5.40. For delta T we can use Celsius or Kelvin interchangeably. Now this is going to be in joules, right? Because we have our heat capacity in terms of joules. So if we want to convert this to kilojoules, which is what the answer is supposed to be in, we can always take this term and multiply it by the conversion factor. So saving a little bit of effort here. That'll cancel out the joules and get us our heat for water in kilojoules. And then finally, for the second term, the heat capacity of the calorimeter is given to us in kilojoules, 9.25 kilojoules per degree Celsius, and we just multiply that by the same change in temperature, 5.40. All right, so those are the two terms, and that comes out to 72.5 kilojoules. Now remember that this heat value represents the heat that's absorbed by the calorimeter, 72.5, and just like we saw in the last problem, the heat for the system, which in this case is the chemical reaction, is just the negative of that. So Q reaction is going to be minus this number, which is going to be minus 72.5. And then finally, if we want to calculate delta H, we want it in kilojoules per mole. So we're going to take that heat of reaction and divide it by the moles of the substance that we burned, in this case acetic acid. Okay? Because of this value here, minus 72.5 kilojoules, that represents the enthalpy change when 5 grams of acetic acid burns. What we're interested in is the enthalpy change in kilojoules per mole, which is the enthalpy change when 1 mole of acetic acid burns. So we divide the two, heat of reaction and the moles of acetic acid that we used, minus 72.5 kilojoules, and then we have to convert the grams of acetic acid into moles. So we have 5 grams, and then we give the molar mass as 60.02. So we have 0.0833 moles. So we divide that in our denominator. Put that in the denominator. And so that gives us minus 870.3 kilojoules per mole. Again, this was sort of set up in the format of a Blackboard problem, so we would just enter in that number in the Blackboard. Okay, so once you have the heat term for the calorimeter, the heat for the reaction is just a negative of that. But then you have to divide by moles of substance if you're trying to get that into kilojoules per mole, as we were here. Yeah? I probably screwed up somewhere. Let's see. I don't think, I can't remember if this is a new problem, if I used this one before. So if there is a mistake here, I probably made a mistake 2 years in a row, and nobody called me on that last year. Okay, so we have that, and then we have, I got that number. So did you do the step here of dividing by 1,000? Because the first term is in joules, so I multiply by the conversion factor. Is anybody else getting a different number? All right. That's okay. It's probably just a rounding thing. In Blackboard, we'll give you like at least a 1% error. So for something like this, if you're within 8 kilojoules, you're fine. So don't worry about that. But we'll have to figure out. I think the numbers are correct. I haven't. As I did? Okay, so by vote of majority, that number is correct. Obviously, if there's something wrong, I'll try to figure it out later. Yeah.
There's a conceptual question that asks Q reaction. If the Q reaction is positive, does that mean that it's exothermic?
If Q reaction is positive, that means it's endothermic. So here the Q reaction is negative. This is an exothermic reaction. So heat of reaction should have the same sign as delta H, just not necessarily the same magnitude, because delta H is usually per mole of substance, and the Q of heat of reaction is really dependent on how much substance you're burning in this case. So if we had burned a whole gallon of acetic acid, we would have gotten a lot more heat out than if we burned just 5 grams, so on. But the sign of that is still negative. The sign doesn't change with the amount of substance. Yeah?
How would you know to divide negative 72.5 by the
So the reason we do this is because the question specifies that we want the enthalpy in kilojoules per mole. And if we had just taken this number, this would be kilojoules per 5 grams, which is not particularly useful finding. So we divide this by moles of substance, and that normalizes it to 1 mole of substance. Anything else? All right, on to number 7. So number 7 asks us to calculate delta H in this case. We're looking for the delta H of formation for B2H6, and we're using the following data. We have 3 reactions here. All right, so this is one of those problems where, it's Hess's law problem. We give you 3 chemical equations, we give you 3 delta H's, and we have to figure out how to combine these 3 chemical equations into some other chemical equation where we're going to calculate delta H. This time we didn't give you the reaction we're trying to compute, though, and that's because it's for the formation of B2H6. So there's 2 types of chemical equations we should be able to generate off the top of our head for this. One is delta H of formation, the formation equation, and the other would be the combustion reaction, which we've seen a lot in this section too. So here we're talking about delta H of formation for B2H6. So a good primer on delta H of formation, a good concept to go over related to that is remember that delta H of formation corresponds to the formation of 1 mole of substance. So we're going to be forming 1 mole of B2H6 as in our overall reaction. And then we form that from the elements in their standard states. So boron is just monatomic boron by itself. And then we're going to combine that with the standard state of hydrogen, which is H2 gas. And then we balance that with 2 and 3 there. Okay, so delta H of formation refers to this specific chemical equation, forming 1 mole of substance from elements in the standard states. So now the question becomes, how do we add these 3 equations together? How do we combine these 3 equations to generate this as our overall chemical equation? All right, so we'll number the 3, 1, 2, and 3. All right, and remember that the approach that we take with this is we look at our chemical equation. Let's start with the first one. And we see that this one has boron as a reactant. Our overall chemical equation has boron as a reactant, and that's the only place that boron appears down here. So we want 2 borons in our overall equation. This one has 4, so we're going to take 1/2 of that first equation. All right, so if we take the first equation and we just multiply the coefficients by 1/2, we get 2 boron. I'll leave out the states of matter, so they don't matter for this type of question, pun intended. And we go to B2O3. Okay, so all we've done is we've taken the first equation and multiplied by 1/2. That gives us 2 borons on the reactant side, which is what we want in our overall equation. And boron doesn't appear anywhere else in the second or third equation, so we know that that's what we're going to have to do to that first equation. If we go to the second one, we have H2 as a reactant, and again, that's the only place that H2 appears in these 3. Our overall equation has 3 H2s. This one has 2 H2s, so what do we have to do to equation 2? 3 would take it up to 6, so how do we change that to a 3 then? 3 halves. So we multiply by 1.5 or 3 halves. So remember, we can take these and multiply them by fractional factors, that's fine. So we take 3 halves times equation 2, so we're going to get 3 H2s plus 3 halves O2. So we have to multiply every single coefficient by the same factor. Now we should also think about what happens to delta H. I kind of lost my train of thought in the first one. So when we multiply by 1/2, the delta H also gets multiplied by 1/2. So the delta H for this modified equation is just 1/2 of that first value there. So it comes out to minus 1254.6. Delta H for this one is going to be 3 halves times the second delta H, because we multiplied all the coefficients by 3 halves. So that comes out to minus 857.6. And then finally, this third equation here, we have B2H6, 1 B2H6 as a reactant. We want it to end up on the product side in our overall equation, so we're going to take this one and we're going to flip it. We're going to take the negative or the inverse of equation 3. So remember, when we do that, we just flip reactants and products. So we have B2O3 plus 3H2O. Those are the products. We flip them over to make them reactants. And then the products are going to be B2H6 plus 3O2. And then the delta H for this, anytime we flip a reaction, we just take the negative of the delta H. So we just change the sign of the third delta H, and that becomes positive 2147.5. So then what we want to do is we add together the three equations. Everything that's on the reactant side carries through, and everything that's on the product side carries through on the product side of our overall equation, and then anything that's on both sides cancels out. So we have 2 borons that carry through. They don't cancel out with anything. For O2, we have 3 halves O2 plus 3 halves O2 on the reactant side. That's a total of 3 O2s, and those are going to cancel out with this 3 O2 that's on the product side. So O2 cancels out. We have 3 H2s that don't cancel with anything. And then in our third equation, we have B2O3 as a reactant, but that's going to cancel out with this B2O3 that's on the product side. And then we have 3 H2Os as a reactant, but that's going to cancel out with the 3 H2Os from that equation. And all that's left on the product side that hasn't already been canceled out is our B2H6. So it's sometimes good to verify that you've added the 3 equations correctly. And if you did, and if you trust yourself to do that, you can just now add the 3 delta H values. So the delta H, which corresponds to delta H of formation, is going to be the sum of those 3 modified delta H values, 1254.6 minus 857.6 plus 2147.5, all in kilojoules, and we should get 35.3, I think. And it's kilojoules per mole because our equation just has 1 mole of B2H6. All right, so that's choice B, positive 35.3 kilojoules per mole. All right, any issues on that one? Yeah.
For the equation 3,
Yeah.
2147, is that 2197?
47. You keep the number the same, you just flip the sign. All right, anything else? All right, number 8 now deals with another sort of application of Hess's law. And so as we kind of already mentioned a little bit in one of the first problems, if we have a chemical equation, in this case it's going to be this one here, the combustion of ammonia to make NO2 and water, we have delta H. We can calculate this delta H value by taking the delta H of formation of the products minus the reactants. So in this situation here, we're looking for the enthalpy of formation for NH3. That's our unknown, and we have the enthalpy of our chemical reaction. So remember that there's this equation that relates delta H of reaction to the delta H of formation for the reactants and products. So the delta H for a reaction is going to be the sum of the delta H's of formation for the products multiplied by their coefficients minus the sum of delta H of formation for the reactants times their coefficients. All right, and the conventional way that we use this equation is we give you a bunch of delta H of formation values for reactants and products, and you calculate delta H of reaction. In this case, we're just doing a little bit opposite. We gave you the delta H for the reaction, and your task is to calculate an unknown delta H formation for NH3, which is one of the reactants in there. Okay, so this delta H of reaction that we're given, minus 1134.4, and I hope you'll, I guess I'll keep units in, just keep, okay, so that's minus 1134.4 kilojoules. That's going to equal the sum of the delta H's of formation for the products. So the products are NO2 and water, and we're given the delta H of formation for both of those. So we have the coefficient of 4 in front of NO2. We multiply that by the delta H of formation for NO2, which is this first number here, 33.2. And then the coefficient for water is 6. This time it's gas phase water. The delta H of formation for gas phase water, which is a little bit different than that for liquid water, is minus 241.8. The delta H formation does depend on the phase, whether it's solid, liquid, or gas. So those are the delta H of formation for the products, and then we subtract delta H of formation for reactants. We have 4 times the delta H of formation of NH3, which is unknown. So that's our unknown. And then our other reactant is O2. So what's the delta H of formation for O2? 0. So remember, anytime you have an element, a standard state element, delta H of formation is 0. So we don't give you this number here, but it's just going to be 7 times 0, 7 moles of O2, but the delta H of formation for O2 is 0. Okay, so we have this is our equation. We only have one unknown, which is delta H of formation for NH3. And assuming I didn't botch my algebra, which sometimes happens, delta H of formation for NH3 is minus 45.9 kilojoules, which corresponds to choice A. All right, so for calculating delta H for reaction, we just have this relatively simple equation here. And like any type of problem, we can either, we have three terms. We could have you calculate any of those terms as long as there's only one unknown. Yep. Oxygen has a delta H of formation of 0 because it's an element in its standard state. So anytime an element appears in your chemical equation, you can basically just ignore it when you're calculating delta H for using formation enthalpies, because the delta H of formation of any element is 0 as long as it's in its standard state. Yeah.
Is it supposed to be F for the product and F for the reactant? Or is that?
Yeah, I mean, those are non-standard abbreviations, but that just means coefficients, and just to make it not seem like it's the same numbers you're multiplying them by necessarily. So this just means you're multiplying each of them by the respective coefficient. Okay. Anything else? All right. Is it? All right, not yet. We're almost time for our favorite problem. All right. So, or did I not give you one? Is there one on here? No. Maybe there's not one on the test. I tried to model this off the test. I hope it didn't mess up. I thought I had one in here, and then I can't remember what I did even yesterday. So I don't know why I'm trying to remember what I did last week when I made this. Okay, so if there's not a last energy problem on here, there probably means there's not one on the test. I will double check that for you, and if there is, I'll email you guys to correct my goof and make sure you study that. But if it's not in here, chances are it's not on the exam. So that's probably a sigh of relief for many of you. All right, so I don't make the test, so don't thank me for that. So thank someone else, Dr. Jan Angel, who usually puts them together. Okay. Anyway, so back to this one. This one's a fun problem. You guys are going to hate it because there's a lot of steps, but I thought it helped sort of understand a lot of different things about conversion factors and things of that. And there is, I think, at least one problem in the exam that you could get that's like this. It's not likely to be one that you have. But we're talking about, methanol, which is a possible fuel for the future. So remember that we talked a little bit about fuels. When you burn them, you release energy, and you can convert that energy into other forms. When we have power plants, we convert it into electricity, and for cars, we convert it into mechanical energy, and so on. So anyway, if we combust, the combustion enthalpy of methanol is minus 715 kilojoules per mole, which means we release 715 kilojoules every time we burn 1 mole of methanol. And it has a density of 0.792 grams per milliliter. If we burn 1 liter of methanol, roughly 1/4 if we're using English units, and we produce electricity that way, how long would it power a 60-watt light bulb if we assume 100% efficiency, which is not a great assumption, but just for this problem we're going to. All right, so if we burn 1 liter of methanol, how long is it going to power one 60-watt light bulb? All right, so we have this important conversion factor here. 1 watt is a joule per second. So when we say that a light bulb is 60 watts, that means it uses 60 joules of energy per second that it operates. All right, if you've taken physics, that's probably a little bit familiar to you. So believe it or not, this has a lot of information, and we're thinking, well, how do you calculate the amount of time that we can burn a light bulb from all this information? We can really set this up in one long string of conversions. So we're looking for the time that this light bulb can burn. All right, our starting point is going to be 1 liter of methanol. That's how much methanol we're burning. And the first thing we should think about is, if we know how much methanol we have and we know the combustion enthalpy, we can calculate how much energy is released when we burn that liter of ethanol. So let's think about how to get this 1 liter of ethanol and convert it into kilojoules or joules of heat. So if we have 1 liter, we should first figure out how to convert it to moles. So that's going to be a few-step process. We have density in grams per milliliter, so we can convert to grams, we can convert to moles. We all know that. So let's first convert into milliliters. Then we can convert into grams using the density. So remember that density is a ratio of mass per volume. So we have 0.792 grams of C4H4O, which corresponds to a volume of 1 milliliter. All right, now we have grams of C4H4O. We can use molar mass to calculate moles. All right, so 1 mole of methanol has a mass of 32 grams. Now we're in moles, so we can figure out how much energy is released when we burn that. So we have 715 kilojoules per mole. All right, and then a watt is 1 joule per second. So if we have kilojoules, we should convert that to joules if we want to relate it to watts. So 1,000 joules per kilojoule. And then finally, we can use this wattage as a conversion factor. So we have a 60 watt light bulb, which means it's 60 joules per second. We want joules to cancel, so we're going to put the 60 in the denominator. So if we divide by the power, that's 1 second per 60 joules. That'll give us the amount of time in seconds. Now, I did write this question, so you can berate me for this. I set this up in a really annoying way with all different units here, so we'll have to figure out what this actually is and a few different things. So this comes out to 2.95 times 10 to the 5th seconds. Hopefully, if you all learn how to tell time in school, you know that there's 60 seconds in 1 minute. So we get 4.9 times 10 to the 3rd minutes, which, if we convert that to hours, is 81.9 hours. All right, so I set this up in a pretty terrible way, but they're all different units. So anyway, the one that matches is choice D, which is 81.9 hours. All right, the rest of these are too small. All right, so a long string of conversions, and it's, a few different concepts tied together. Hopefully this makes a little bit of sense. And this tells us then if we have 1 liter of methanol, we burn it, we can power our light bulb for about 3 days. All right, so this reveals that yes, these liquid fuels do have a lot of energy stored in them, but also if we think about how many 60 watt light bulbs we have to burn to power our city or our planet, we have to burn a lot of fuel to do that. So kind of a fun one to think about from that standpoint too. All right, questions on that? All right, moving on to number 10. So now we're going to start talking, if we're sort of keeping track of where we are in terms of the progress. These are going to be problems that mostly deal with Chapter 8, which is gas laws. The overall breakdown, again, is going to be very similar to what we have in the practice exam that I've given here. So for the exam, it's going to be, as I said, Chapter 7, Chapter 8, and then about half of Chapter 9 up to 9.6. It's going to not be evenly distributed, though. So you're going to have probably between Chapter 7 and 8, roughly 16 of the 20 questions, and then only maybe 3 questions on Chapter 9. So you'll definitely want to focus most of your effort on Chapters 7 and 8, but there's a few things from Chapter 9 that'll come up as well. So now we're into Chapter 8, which is gas laws. All right, so here we have a balloon that's filled with an ideal gas, has a volume of 253 milliliters at 24 degrees Celsius. What is the volume if the temperature is increased to 86 degrees Celsius? So there's a lot of different variations on this type of problem, which is where we have a sample of an ideal gas, we change one parameter or more than one parameter, and we try to calculate how another value responds to that. So anytime we're doing a problem like this, we start with PV equals nRT. And then the variables that are changing, we move them to one side. The variables that are not changing, we move them to the other side. So we just do a little bit of algebra on this equation and rearrange it. So in this case, the volume and the temperature are changing. So we put V over T on one side, and then we put everything else on the other side, and those are going to be all constant. And so that means the two variables that are changing, V and T, we can set this ratio equal. V1 over T1 equal to V2 over T2. This is an expression of Charles' law. It's helpful to know the names of these, but again, the equations can all be derived from PV equals nRT. So V1 over T1 equals V2 over T2. And so what we're solving for is the final volume, which we'll call V2. And that's going to be V1 times T2 over T1. All right, so there's a direct relationship between temperature and volume. As you increase the temperature, the volume also increases. And so now you have to start plugging in numbers. The important part for all these ideal gas law problems, we're not dealing with change in temperature, we're dealing with absolute temperature, so the temperature has to be in Kelvin. So our T1 is 24 degrees Celsius, but we have to add 273 to that to get 297 Kelvin. And then T2 is 86 degrees Celsius. which corresponds to 359 Kelvin. All right, so when we plug these in, we have our V1 is 253 milliliters. The other nice thing about setting up the equation, the problem this way, is that we don't really care what units we use for anything except for temperature. So as long as the two temperatures are in Kelvin, this will work out. So Kelvin divides out. That gives us a final answer, which is also in milliliters, which is what we want. And this comes out to 306. Which is choice C. All right, so even though we're raising the temperature from 24 to 86 degrees Celsius, your first thought might be, oh, we're tripling the temperature. But remember that it's absolute temperature that matters. So even that relatively large temperature change on our scale was really only about a factor of, 20% or so in the volume. So the volume only increases to that value there. Okay, yes?
Should we always put temperature in Kelvin?
Yeah, for especially for ideal gas law problems, temperature has to be in Kelvin. Yeah. Yep. So the questions where you don't have to change it to Kelvin are when you have a change in temperature delta T. Because when you're talking about delta T, you're subtracting two temperature values, and whether you have the two temperatures in Celsius or Kelvin, the difference between the two is the same. So as an example, if we're talking about delta T, let's say we're using these two temperature values. Delta T would be 86 degrees Celsius minus 24 degrees Celsius, which is 62 degrees Celsius. Or if you did it in Kelvin, delta T would be 359 Kelvin minus 297, which still equals 62 this on Kelvin. So when you're talking about a difference in temperatures, whether they're both in Celsius or both in Kelvin to start, you get the same difference, 62. But when you're plugging in an absolute temperature into an equation, like in this exam it's going to be PV equals nRT, or the more recent stuff that we covered in class with vapor pressure that won't be on the exam, anytime it's just temperature by itself, it has to be in Kelvin. Okay? But it never hurts to convert into Kelvin. If you just want to remove all sources of doubt and always convert it into Kelvin, you're welcome to do that. All right? Good. All right, number 11 is a similar type of problem. So this time we have a steel tank, which means the volume is fixed, and we fill it with 126 grams of nitrogen at 298 Kelvin, which gives us a pressure of 235 kPa. What will be the new pressure if 96 grams of nitrogen is added and the temperature cools to 273 Kelvin? All right, so here if we start with PV equals nRT, we'll notice that the pressure is changing. That's what we're trying to calculate. And then we have the number of moles changing because we're adding more gas, and the temperature changes from 298 to 273. So those three things are all changing. So once again, we move them to one side of the equation and derive sort of a non-standard form of the equation. P over NT equals R over V. And that means P1 over N1 T1 equals P2 over N2 T2. Now this equation doesn't have a name associated with it, but it's a valid equation that we can derive starting with the ideal gas equation. Okay, so what we're solving for is P2, which is going to be P1 times N2 T2 over N1 T1. And so now we have to start plugging in numbers. The P1 is the initial pressure which is given to us, 235 kPa. We're trying to find the final pressure in that same units. So we want to just keep that the same, 235. We don't need to convert that to anything. One thing we should be aware of that I only mentioned briefly in class, but it could come up on the exam, is that 1 atmosphere is 101.3 kPa. You can this is the SI unit, so you can get that by dividing. Anyway, so that conversion factor could be important as well, but we don't need it here, so we're going to keep it in kPa. All right, sorry. Back to the task at hand. So now we need the number of moles of each. So N1 is the amount of moles that we start with. We gave you grams of nitrogen, so we can convert that into moles just by using molar mass. So we're starting out with 4.50 moles of N2. mass to moles conversion that we've been doing for many months now. That's our N1, and then remember N2 is going to be, we're adding 96 grams of N2. So N2 is going to be the sum of the two. So whenever we're talking about PV equals nRT, this is not the amount that's added. It's going to be the total amount that we have at the end. So we have to combine the two. We start with 4.50 moles, and then we're adding to that 96 grams, which we convert to moles using also the molar mass. All right, so this 96 grams that we're adding, we have to combine that with the first amount to get the number of moles that we have at the end. So the sum of those two is 7.93 moles. So we're adding about 3.43 moles to that. Okay, so that's going to be N2, the combined amount that we have at the end. And then T2 is the final temperature, which is 273. And then we divide that by the initial number of moles, which is 4.50. And T1, which is 298. All right, so with all that stuff changing, what we end up with is a final pressure of 379.4 kilopascals. In Blackboard, we would just put the number in. Okay. All right, so it's just another gas law problem, a little bit more going on here because we have three variables that are changing. But once again, we just rearrange the ideal gas equation to find the new form of the equation that we're going to use. Okay, questions on this? All right. If you were to change it to atmospheres, you could then, you would plug that pressure in here, and then your final answer would also be in atmospheres, and you have to convert it back. Right, so we tell you kPa in parentheses. So anytime we're having you fill in the numbers, we'll tell you what units you have to use. So we do specify that, and remember you don't type the units in, you just type the number. Okay? Yeah.
Is the 101.3 equals 1 ATM? Is that on the sheet before?
Not exactly. It also comes from, it's the same number that you convert joules into liter atmosphere, because this is SI units and this is non-standard units. So it's related to that. It's the same conversion factor, but it's not directly on the conversion sheet or on the periodic table. So you'll have to remember that possibly. All right. Other questions? All right. Number 12. All right. So this one is a gas stoichiometry problem. We're taking two gases and they're reacting to form a third gas. If we start with 32.5 liters of NO and treat it with 21.2 liters of Cl2, how many liters of the product NOCl form? All right, so this is a stoichiometry problem because we're taking amounts of reactants and converting them into amounts of products. And so the first step in any stoichiometry problem is to write a balanced chemical equation. So we have NO plus Cl2, and then we have NOCl. So if we want to balance this, we have two Cl's on the reaction side, so we'll put a 2 here, and that gives us a 2 there. So pretty simple to balance by inspection. Coefficients of 2 there and there. Make sure it's balanced before we start. All right, so we have a stoichiometry problem. We have amounts of both reactants. So if we have the amount for both reactant, what's the first thing we do before we start doing any wild calculations? We have to find the limiting reactant, right? So we're going to have to do that here. Now we should recognize something else that I didn't probably say in class, but I've covered in some of the reviews since then. STP, which we'll see on the exam sometimes, that's standard temperature and pressure. Which means 1 atmosphere and 273 Kelvin. Okay, so whenever you see STP, that tells you what the pressure and the temperature are right away. That said, we don't really need to even think about that for this question. So when you have gas stoichiometry problems, there's often multiple ways you can do it. So we're used to working with moles for all of our stoichiometry problems. 2 moles of NO react with 1 mole of Cl2 to make 2 moles of NOCl. However, when we're dealing with gases, remember that from the ideal gas equation, PV equals nRT, pressure, volume, and moles are directly related. So moles is directly related to volume, moles is directly related to pressure. So if we tell you the volumes of each gases that are reacting, we can interpret the coefficients in terms of volumes as well. So for an ideal gas, we could read this equation as 2 moles of NO plus 1 mole of Cl2 makes 2 moles of NaCl. Or we could read it as 2 liters of NO reacts with 1 liter of Cl2 to make 2 liters of NaCl. So for gas phase reactions, you don't necessarily have to always convert into moles because the mole ratios and the volume ratios are going to be equivalent for any time things are reacting in the gas phase. That said, we still have to determine a limiting reactant, but we don't necessarily need to convert all the way to moles to do that. We could convert to moles, but it would be a lot of extra steps for us, especially since what we're looking for is the volume of the product in liters. So first we determine the limiting reactant. And so all we do for that is just take, remember we determine these stoichiometric ratios. We take the volume of each gas and divide it by the coefficient because the coefficients are also volume ratios in addition to being mole ratios. So 32.5 liters of NO, we divide that by the coefficient, which is 2. So the stoichiometric ratio for NO is 16.25. And then for Cl2, we do the same thing. The volume of Cl2 that we're starting with, which is 21.2, divided by the coefficient for Cl2, which is just a 1. And so that comes out to 21.2. So this is the smaller number, so this is going to be the limiting reactant. All right, so now our calculation is going to start with that. We're going to start with volume of NO as our starting point. So if we're looking for the liters of the product NaCl that can form, we're starting with 32.5 liters of our limiting reactant, 2 liters of NaCl divided by 2 liters of NO because we have coefficients of 2 for both of them. So for every 2 liters of NO that react, we're forming 2 liters of our product, so they react in a 2-to-2 ratio or 1-to-1. And so that means the volume of product that can form is that same number, 32.5. Okay? So for gas stoichiometry problems, a lot of times you can save yourself work if you realize that these mole ratios are equivalent to volume ratios. Another helpful shortcut for you on some of these types of problems is that, and I hesitate to give you this because it only works at STP, but if you're at STP, if you're under those very specific conditions, 1 mole has a volume of 22.4 liters. So if we had been asking you about moles of product or masses of product which required us to use the moles, we could have just divided these numbers by 22.4 to get the moles. We wouldn't have to necessarily even use PV equals nRT. But just remember that we can only use this conversion factor at those specific conditions STP. Otherwise, you have to use the full equation, the ideal gas equation. Okay, questions on that one? Okay. All right, number 13. A 250 milliliter gas bulb is filled with 0.379 grams of a gas at STP. Which of these is most likely to be the gas? All right, so again, STP tells us that we have 1 atmosphere and 273 Kelvin. So we have the temperature and pressure, we have the volume, and we have the mass. Now we've seen a few different problems in this course that ask us to identify unknown substances, either atoms or molecules or elements or compounds. And typically what we want to look for in that case is the molar mass. If we can calculate the molar mass of these substances from this information, then we can identify which one of those matches best. So first let's keep in mind what the molar masses of all these are, at least in approximation. So pH3 would be 34, if it's just phosphorus plus 3 hydrogens. This one's about 64, 32 plus 2 times 16. This one, as we've seen, is 28. And this one is about 40. So basically what we're going to do is we're going to try to use the given information in the problem, and then we're going to calculate the molar mass and see which one of those matches up most closely. So there's a couple ways that we can do this. If we keep in mind that molar mass is just mass divided by moles, if we can find both of those, then we're able to get the molar mass. So we have our mass is given. We have a bunch of parameters for the gas. So we can use PV equals nRT to find the number of moles. All right, so if we find the number of moles of this gas that we have, now I didn't initially do it this way, but so I'm going to have to do this calculation in a second. But we have 1 atmosphere as our pressure because we're at STP. We have our volume is 250 milliliters, which needs to be converted to liters for the ideal gas equation. Then we divide by RT. All right, so we're using PV equals nRT to find out how many moles of gas we have because we have all the other variables given to us. And I didn't calculate this initially because I did it a different way, so let me get this real quick. All right, so what I got was 0.0112 or somewhere around there. I guess I could have used the shortcut that I showed you guys before, which is 1 mole is 22.4 liters. Does that give you the same number? Yeah. Okay. So either with PV equals nRT or with the shortcut that I told you about before, by just converting volume into moles, we can get that number. This is the number of moles, and then the molar mass is going to be the mass divided by that. So we're told that that's 0.379 grams. That corresponds to 0.0112 moles. And so we divide those two. A second. And what we should end up with is, if we do it to a bunch of sig figs, 33.98. Okay, and that corresponds most closely to choice A, which is phosphine pH 3. Alright, we could have done this in one step also. We could have replaced, remember when we derived the density equation, we could have replaced this with mass divided by molar mass, and then solve for molar mass in one step. So there's a couple of ways to approach this one. I thought this might be a little bit friendlier to understand, so I did it this way today, but you could have done it in one step as well, and either way you'll get that molar mass, which identifies most closely with pH 3. Alright, questions on that? So this is very closely related to the density equation, which is just derived from PV equals nRT. So remember, you can rearrange things and get density as pressure times molar mass over RT. So this is a very related concept. We're using, in some sense, this type of idea where we're converting moles or thinking about moles in terms of mass and molar mass. Okay. Alright, number 14. We have a tank which contains 3.25 atmospheres of N2 and a volume of 9.3 liters. And then we connect that to another tank which has 5.33 atmospheres of O2 with a volume of 15.2 liters. So the valve that separates the tank is open, which allows the two gases to mix. We want to know what is the final pressure after they have mixed. And we're telling you that no chemical reactions occurs and the temperature is constant. Alright, so we should recognize this as a Dalton's law type problem where we're trying to find the total pressure of a mixture of two gases. So whenever we have a mixture of gases, the total pressure is just the sum of the partial pressures. But what we have to be a little bit careful with here is that we can't just simply add together the two pressures that we're starting with, 3.25 and 5.33, because once we mix them, the partial pressure of N2 is going to change because it now occupies a larger volume, and same with the partial pressure of O2. So these partial pressures that we have to use in this case is going to be after mixing. Alright, because once we mix the two gases, they occupy a larger volume because then now it's the combined volume of the two tanks. And so the partial pressures of each is going to change from what they initially are when they're separated and not mixed together. Okay, so I'll do that. Alright, so what we have to do is for each gas, we're going to use the ideal gas equation to figure out what the new partial pressure is after they mix together. So for each gas, PV equals nRT. The number of moles of that gas is not changing. We're telling you that the temperature is changing, so for each gas, we're going to use Boyle's law. P1V1 equals P2V2. Where P1V1 is the pressure and volume before we allow the gases to mix, and then P2V2 is the partial pressure of that gas after we allow the gases to mix. And so for each one, we're going to solve for P2, which is just going to be P1V1 over V2. All right, so if we do that for nitrogen, which is the first gas, the final pressure after mixing, the initial pressure for nitrogen is 3.25 atmospheres. The initial volume is 9.30 liters. And then after we mix them together, the final volume is going to be the sum of the two volumes that we start with. So the gas can occupy the full space. So V2 for both of them is going to be the sum of the two volumes. 9.30 liters plus 15.2 or 24.5. So the partial pressure for nitrogen after mixing them together is 1.23 atmospheres. And then the partial pressure for O2 after mixing, we have 5.33 atmospheres of O2 to start with. The initial volume for O2 is 15.2. And then the final volume, again, is the combined volume, 24.5, which comes out to 3.31. All right, so those are the two partial pressures of the gases. This is for O2. Those are the two partial pressures for the gases after they're allowed to mix together. So now we just add those two numbers together to get the total pressure after mixing. All right, so that would be choice D in this case. All right, any problems with that one? So you would add them together if you're just mixing two gases into a fixed volume. So if we had just, if we had 3.25 atmospheres of N2 in a 9.3 liter container, and then we just added in 5.33 atmospheres of oxygen and the volume didn't change, then you would just add them together. But in this case, once we mix them, the gases are able to occupy the full space, which is the sum of the two volumes. And so you have to first determine the partial pressure after mixing and then add them together. Yeah. Yeah, that'd be mathematically equivalent, because what you're essentially doing is, for each of these terms here, the partial pressures is going to be, it's going to be the partial, is this what we calculated here, plus the same thing for O2. Yeah, and then they have the same denominator, so you can combine them. Yeah. So they're mathematically equivalent, and it's fine if we want to do it that way. One thing we're starting to notice with gas law problems especially is that there's often more than one way to approach it. As long as what you're doing is scientifically valid, then be my guest, do it however is most comfortable for you. So that would be a perfectly valid way to do this as well. It's just to combine the two beforehand and then derive a new equation that includes them both. All right? 15. Sorry, do we have another question over here that I missed? No. Okay. A 2-atmosphere sample of N2 effuses through a small opening in a time of 2 minutes. So remember, effusion talks about leaking. So that's saying if we have, a 2-atmosphere pressure of N2, it takes 2 minutes for it to leak out completely. And then we have a sample of unknown gas under the same conditions, which takes 3.9 minutes. This should be effuse. It should be both the same word. Sorry about that. What is this molar mass? Either way, whether they're talking about diffusion or effusion, the equations are the same. So what we have to remember, though, for these ones is that there's really only one equation, but there's two forms for it. So the standard form of this equation is in terms of rate. So if we were comparing the rate of, let's say, N2 to the rate of our unknown, that would be related to the inverse square root of the molar mass ratio. So you have molar mass of X over the molar mass of N2. All right, so if you're talking about the rate of effusion, they're inversely related. In other words, the heavier the gas has a slower rate, and the lighter gas has a faster rate, so there's an inverse relationship between rate and molar mass. However, when we have times, which we're given here, so here we're telling you how long it takes for them to fuse, time and rate are inversely related. So the one that has the higher rate is going to take a shorter amount of time. The one that has the smaller rate is going to take the longer amount of time. So if we're thinking about the equation in terms of the time that it takes to effuse or diffuse, we have to invert one side of our equation. So if we keep the left side of the equation same, N2 divided by our unknown, then the right side of the equation has to be inverted, where it's now going to be directly related. Okay, so there's two forms of this equation. Whether we're talking about rates or whether we're talking about times, you have to be able to you have to flip one side of the equation when you're dealing with time as opposed to rate. Okay, so that's the equation we want to use. So now we start plugging in numbers. So it takes N2 2.0 minutes to effuse. It takes our unknown 3.9 minutes. Now thinking about this conceptually for a second, if our unknown gas takes longer to effuse than N2, that means it should be heavier than N2. The heavier that a gas is at a given temperature, the slower that it moves, the slower that it effuses or diffuses, so it would take a longer amount of time. So we should get a number that's bigger than the molar mass of N2, so hopefully that works out. And now we can rewrite this whole thing as just a ratio of two square roots. So the square root of the molar mass of N2, which is 28.0, and then the square root of our unknown. Alright, so now we just have to square both sides and then cross multiply. Again, for a review like this where we're already stuck here for a long time, I won't go through the algebra. The molar mass of Exo should come out to 106 grams per mole. Alright, and like I said, it should be definitely bigger than N2 because the gas takes longer to effuse. So even before starting the problem, we could have eliminated choices C and D just by thinking about it conceptually. But the one that works out is 106 when we solve this for the unknown molar mass. All right, so for effusion and diffusion, there's just this one equation, but remember that there's two ways we can write it. Yeah. It doesn't matter. So we can write the equation with either compound on top or bottom as long as we flip the other side of the equation, of course, as well. And then it probably actually would have worked out better. The algebra would have been easier if I flipped this. It's kind of hard to have that foresight when you're starting a problem, so I just randomly started a problem like this, and now my unknown's in the denominator, which makes the algebra a little bit trickier. So yeah, if you could have flipped both sides and you would have still gotten the same answer with even slightly easier algebra in that case. Anything else? All right, we're on the home stretch. If you're running a 400-meter dash, we're on the home stretch. Okay, so which of the following statements about ideal gases is false? All right, so for kinetic molecular theory, that's one of the sort of subtopics we talked about in Chapter 8, which is the atomic or molecular level picture of gases. There's going to be problems like that, which deals with their rate of effusion, rate of diffusion, things like that, and then there could be some conceptual things as well, where we have to sort of understand the properties of ideal gases and some of the theoretical basis behind that. All right, so again, this is one of those fun problems where you have four statements. You have to figure out which ones are false. Okay, so let's evaluate them one at a time. In a mixture of two gases A and B, the total pressure depends only on the total moles of A and B, not their identity. All right, so this one, remember from the ideal gas equation, PV equals nRT. There's nothing in this equation about the identity of the gas. All that matters is how many moles of it you have. And furthermore, we know from Dalton's law of partial pressures, when we mix two gases together, as we saw in the problem just a couple slides ago, when you mix two gases together, it doesn't matter whether they're two of the same gases or two of the different gases. The total pressure is just determined by the total number of moles of gas that you have. So it doesn't matter what they are. As long as you know the number of moles, you're going to get the pressure from the ideal gas equation. So that one's going to be true. We're looking for the false statements in this case. So that one's one of our true statements. For choice B, all right, so here's an important point about kinetic molecular theory. We have samples of helium and O2 at STP, so same temperature and pressure. Will they have the same average kinetic energy? Okay, so the average kinetic energy depends on only one thing, so don't try to think about this any harder than you need to. The average kinetic energy is a function and directly proportional to temperature, and that's it. So if the two gases are at the same temperature, it doesn't matter what they are, they will have the same average kinetic energy. All right, so kinetic energy only depends on temperature. If both gases are at STP, they're both at the same temperature, that means they have the same average kinetic energy, so that one is also true. Okay? So when talking about kinetic energy specifically, only kinetic energy, you just have to think about temperature. Now choice C goes a little bit in more depth. We have same samples, helium and O2 at SCP. Do they have different or same molecular speeds? And if they are different, is O2 higher? So this one's saying that they're different, with O2 having a higher molecular speed. Okay, so remember that at a given temperature, kinetic energy is equal to 1/2 times mass times the average of the square of the velocity. And as I just said, that's proportional only to the temperature. So these two gases have the same kinetic energy, but if they have the same kinetic energy, they can't have the same velocity, because the heavier gas is going to have the smaller velocity, the lighter gas is going to have the higher velocity to make sure they have the same kinetic energy. All right, so in other words, the velocity is going to be proportional to 1 over the square root of the temperature when we solve for that. Okay? So, sorry, not the, ooh, man, Tom. Molar mass. All right. I don't want to confuse you guys. Okay, so the velocity is proportional to 1 over the square root of the molar mass. That's where those effusion and diffusion equations come from. So when you have two gases at the same temperature, the one that is lighter is going to be moving faster, the one that's heavier is going to be moving slower. So O2 is heavier than helium. O2 has a molar mass of 32. Helium is only 4. So O2 should have the slower speed in this case. So this one is one of our false statements. We're looking for the false statements here. So that one's false, because I should write T, F. Okay, and then finally for choice D, deviations from the ideal gas law are smallest at high pressure and low temperature. Now remember that the smallest deviations from ideal gas law occur when the gas particles are as far apart from each other as possible and when they're moving as fast as possible. So the smallest deviations are going to actually occur at low pressure, that's when the molecules are far apart from each other and not interacting, and at high temperature when they're moving as fast as possible and also not then interact with each other for any long period of time. So choice D is completely opposite of that. That one is also false, because this one says that the deviations are smallest at high pressure and low temperature. It should be the opposite case. All right, so the answer for this one would be E, where both C and D are false statements. Okay, questions on those conceptual topics? All right, the last three that we have to go through now are little slice of chapter 9 that we have. And as you'll see, we don't go into really great depth on any of these topics because they're pretty much purely conceptual, especially at this stage. And we just kind of want you to know the basics of these. We're not going to give you a lot of really detailed questions. All right, so the first one here is, which intermolecular forces are present in a sample of SF4? All right, so we have a few choices here: London dispersion forces, covalent bonds, dipole forces, or is it two of these, or is it all of these? Okay, so we have really three things we have to consider. So London dispersion forces, which are also sometimes just called dispersion forces, sometimes the London part is left out, or just called London forces. Those three all mean the same thing. Those are present in everything. Okay, so this one we can automatically check off because everything experiences London dispersion forces. As long as it has one or more electrons, which all matter does, unless it's a proton by itself, everything has London dispersion forces. So that one you don't even have to think about. If you're asking a question like this, which is which forces are present, that will always be there. Now you think about the other ones, covalent bonds. Remember that covalent bonds is not an intermolecular force. This compound does have covalent bonds. It's a covalent compound, but that would be an intramolecular force, not an intermolecular force. Okay, so remember that IMFs, as we abbreviate them, or intermolecular forces, those are the weaker forces that are responsible for holding individual molecules together into a condensed phase, that are responsible for attractions between molecules. Covalent bonds are the forces that hold the molecules together, the atoms in the molecule, so that's not an intermolecular force. So we don't want to confuse this with bonding. When we're talking about intermolecular forces, we're only talking about either London dispersion forces, dipole forces, or hydrogen bonding. Those are really the only three types of intermolecular forces. So then the last choice is dipole forces. So we have to figure out if this substance has dipole forces. And really, to have dipole-dipole forces, it just has to be a polar molecule. So we have to figure out if this molecule is polar or not, so that kind of takes us back to a review of Chapter 4 topics. So for dipole-dipole forces, we need to have polar molecules. All right, so for SF4, we have to figure out if it's polar or not, so let's draw the Lewis structure. Sulfur has 6 valence electrons, is in group 6. Fluorine has 7, there's 4 of them. So this compound has 34 valence electrons. So when we draw the structure SF4, when we complete the octet of fluorine, 6 non-bonding or 3 lone pairs each, that's 32 electrons, so we have 2 more to put in the central atom. So this is AX4E, and without even considering the geometry of this molecule, anytime you have 1 lone pair in the central atom, it's polar. So this one, it gives us a seesaw geometry, but because there's 1 lone pair, it must be polar, so that means it's going to exhibit dipole-dipole forces. So 2 of those are going to be correct, London dispersion and dipole-dipole. The third type of intermolecular force, so IMFs, we have London dispersion, dipole-dipole, and then the last one that you could see is hydrogen bonding. Remember, hydrogen bonding is just a specific type of dipole-dipole force where you have hydrogen bonded to a really electronegative element. So if you have NH bonds, OH bonds, or HF bonds. So this compound doesn't even have hydrogen at all, so it clearly can't have any hydrogen bonding if that was one of our choices. But if your compound does have covalent bonds between hydrogen and one of those 3 electronegative atoms, nitrogen, oxygen, fluorine, then it will also exhibit hydrogen bonding, which is a stronger type of dipole-dipole force. All right, questions on IMFs, intermolecular forces. This is a pretty recent topic, but like I said, there's not a ton of details here, just a few things we want to be aware of from a conceptual standpoint. All right, so then number 18 deals with which of the following does not increase with the strength of the intermolecular forces. So the intermolecular forces are important because they determine some of the key properties for for molecules. All right, so there's a few major properties that IMFs are directly related to, which means if the intermolecular forces increase or get stronger, then these properties also increase. So they're going to be related to melting point, boiling point, viscosity, surface tension, and the last one, which probably won't show up on this exam, but is related to things we talked about more recently, is vaporization enthalpy or fusion enthalpy. All right, so in other words, the stronger the intermolecular forces are, the higher or the larger all these properties are. So stronger IMS means the melting point will be higher, stronger intermolecular forces means the boiling point will be higher, the viscosity will be higher, the surface tension will be higher, and the delta H of vaporization or fusion will be larger. So IMS determines all those properties. However, so this one, these are all correct. And so it does not increase with, what does not increase with the strength of the intermolecular force would be E, ideal gas behavior. Okay, so remember that for ideal gas behavior, stronger intermolecular forces gives us a less ideal gas. And that's because the ideal gas law assumes that there are no interactions between gas molecules. And so if the intermolecular forces are actually quite strong, you have strong interactions between those gas particles. They're not going to behave as much like a gas. Okay, so if you have stronger intermolecular forces, you're going to have less ideal gas behavior. You're going to have more deviations from the ideal gas law, is another way to say that. Okay, questions on this one, things that are related to intermolecular forces. Okay, so then the last one here we have, or no, sorry, 2 more. we're talking about cubic unit cells in this case. We have a partially filled cubic unit cell that has 4 corner atoms, 2 face atoms, and 4 edge atoms. Alright, so remember that in a cubic unit cell there's 4 places we can put atoms, at least that we've talked about. So we have a cube. Alright, so when we have a cubic unit cell, there's 4 places we can put them. One is right in the center of the cube, which is a little bit hard to draw. But we can also put atoms right on the face. Now this is ignoring those holes that we'll talk about later. So remember, for this exam, we're only going to talk about the positions on a either face-centered or body-centered cubic lattice, or we're not going to talk about the ionic compounds in this one. But we do have to know how to count atoms on a cubic lattice. So you have face-centered positions. I'll do it in a different color. We have corner positions. And we have edge positions. All 3 of those we're considering in this problem. See that? Try to do that different color. All right, and then each of these are going to be shared by neighboring unit cells, because when we build up a crystalline structure, we're taking this cubic unit cell and we're stacking it in all directions. So any atom that resides in these positions is going to be shared by other neighboring unit cells. So the face is going to be shared by 2 cells. The corner is going to be shared by 8. There are 8 cubes that would share 1 corner. Think about stacking blocks if you want to think about it that way. And then the edge is going to be shared by 4. Alright, so when we're counting the atoms that would be present in this unit cell, we would count a face as 1/2 because it's shared by 2 different unit cells. We count a corner as 1/8 because it's shared by 8 unit cells, and we count an edge as 1/4 because it's shared by 4 unit cells. So for this one, if we want to count the total number of atoms, we have 4 that are in the corner, and those are each going to count as 1/8. We have 2 faces that each count as 1/2 because those are shared by 2. And then we have 4 on the edge as well. So in that we have 2.5 atoms per unit cell when we count these up. Okay? So this is not really a situation you would normally see in a stable crystal structure. You don't typically have partially filled unit cells. But if we want to learn how to count the atoms that are in a unit cell, we have to know that the differences between corner, faces, edges, and then if we put an atom at the center of the unit cell, that counts as a full atom because it's not going to be shared by any. Okay, questions on that topic? All right, like I said, there's a table in the notes when we introduce this that has, the different types of cubic unit cells and the number of atoms in there, and other things related to that. Relative packing densities, you don't have to know the specific numbers, but relative packing densities of those kind of concepts we're going to ask you about, but not in any great detail. All right, ready for the last one? All right, so the last one here is we have an element is found to be a good conductor of electricity, has a high boiling point, and is malleable. Which of the following could be that element? All right, so here we're talking about the properties of an element. We want to know what it was related to. So remember, for elements, we really only have 2 major types: metals and nonmetals. Probably should have given you the chemical symbols for some of these because they're kind of low on the periodic table. All right, anyway, we're going to compare metals to nonmetals. So we want to know which of these types of properties is this more similar to. So metals and nonmetals differ with respect to their electrical conductivity. Metals are conductors, and most nonmetals are insulators. Not all, but most. They're also different with respect to their mechanical properties. So mechanical properties is when you have a solid piece of that element and you, let's say, hit it with a hammer, what happens to it? So metals are malleable, which means that they tend to bend They don't really shatter. They bend when you hit them with a hammer. They deform, but they don't break. And then nonmetals tend to be brittle. All right, so if you took, for example, iodine is a nice purple crystalline solid. If you took a big piece of iodine, put it on the table here, and then I hit it with a hammer, it would shatter into a million pieces, and then very quickly we'd have to evacuate the room because the iodine vapors would go everywhere and poison you guys. But for that period of time, it would be a cool demonstration before we all started choking and dying. It's not that bad, but it's volatile, so we want to be careful with that. Okay, so then metals are, in terms of their boiling points, are high boiling. Okay, because we talked about the metallic bonding model, which is that the atoms in a solid piece of metal are held together by all these delocalized electrons. They're all attracted to each other through that sea of electrons. And in order to boil them and bring them into the gas phase, you have to break some pretty strong metallic bonds. So they tend to be high boiling, but then high boiling points is a more specific way to say that. And then nonmetals tend to have low boiling points. All right, because as we know, the standard states for most nonmetals is gases, which means they boil at very low temperatures. They exist as gases at room temperature. All right, so that's sort of the differences between nonmetals and metals. So if we have an element that's a good conductor, has a high boiling point, and is malleable, it must be a metal. So which of these 5 elements is a metal? When you go to the periodic table, if we don't remember where they are, where's that periodic table? It's not there anymore. Thanks. I'm losing it. It's the end of the semester. I'm fizzling out. Okay. Well, yeah, I'm sure you guys are too. All right, so we have to find these on the periodic table, figure out if they're metals or nonmetals. All right, so sulfur, phosphorus, neon are the first 3. Those are all nonmetals. Sulfur, phosphorus, neon, they're all on the right side of the periodic table, on the right side of the imaginary staircase, so they're nonmetals, so they don't fit. Then we have gold and iodine. Iodine is also a nonmetal. It's way down here in the lower right. And then gold, which is a transition metal. I can't see it from this angle, but it's right there. 79. So gold is in the transition metal series, so it's going to have those metallic properties. We should recognize that gold is pretty shiny, pretty malleable, all those typical properties you associate with a metal. So this description best matches gold, which would be a metal. All right, questions on classifications or properties of substances? All right, hope the exam goes well for all of you. If you have any last-minute questions, over the weekend, you can contact me by email, or next week you can come visit me either way, and we'll get those addressed. All right, see you guys on Monday.